Hey everyone, today we'll be solving ABC 283. So let's get started with problem A straight away. So the problem A was named power, and in this question we have to find A raised to B. Now, first of all, let's see what is actually meant by this notation. So A raised to B. So this simply means that you have to multiply A by itself B times. So let's take an example to understand this better. So if I say that I have to find 2 raised to B, that means a third power of 2, then this is equivalent to multiplying 2 by itself 3 times. Oops. 2 by itself 3 times. So this will be equal to 8. Now this problem is really straightforward, since also there is one thing that any number raised to power 0 is going to be equal to 1. But as the constraints show us, this case is not going to be encountered in this question. So all that we have to do is run a loop b times and multiply a with itself those many times. So let's jump onto the code right away. So here's the code from the problem. We first of all take in the input in integers a and b, and then we take p as the answer. That means the calculated power is denoted by p. We run a loop b times and we simply multiply p with a, and then we output the answer. That's going to be the p. So we noticed that we were able to solve this problem in linear time complexity. That means that we were running a loop that ran b times. So basically, it was a big O of b times complexity. So that means that our time complexity here was equal to O of b. Now, since b was really less, that means it ranged only from 1 to 9. So this was really easy. Now, what if B range is say very big? So for example, 10 raised to 8, or maybe larger than 10 raised to 8, or maybe till even 10 raised to power say 18 or something like that, where we cannot actually run a loop till this. So there is a really handy and nice concept known as binary exponentiation. So something called as binary exponentiation. Try reading about it. It's really cool stuff, and you will be able to find power of any number in log of b time. So we'll not be discussing it here as of now, but let me know if you have any difficulties or you want a specific video about it. Now we'll be solving problem B. Here's the problem statement. You're given an integer n and a sequence A of length n. Okay. Given q queries, we have to process them in the given order. Each query is one of the following two kinds. So the query can be of two types. So first of all, we are given A, which is a sequence and has n as its length. Okay, and then we are given q queries, which can be of two types. So let's see. So first query is 1kx. Okay, that means that we have to set the value at index k equal to x. Okay, so here's the first type, in which we are given the query type as 1, and it will have two integers k and x. In this one, we have to set the number which the kth number of our sequence equal to x. Okay, and then we have the second type of query, in which we have to simply print the value of a in ak, which means we'll be given k and we have to tell what number is currently present as the kth number of the sequence. So the question is again pretty straightforward and can easily be solved using the one of the most basic data structures. Yes, you guessed it correctly. The name of that structure is an array, or maybe you can call it a vector. So that's exactly what this data structure does, and we don't need to do any special kind of stuff, just that we are given k as one based indexing. So k will be given as index base 1. So this is basically our index, and the answer will be pretty straightforward. We can simply maintain an array, and whenever it's type 1 query, we can simply assign a of k minus 1 equal to x, and whenever it's of kind 2, we can simply print a of k minus 1. So let's hop onto the code and see the implementation. So first of all, take in the sequence size, then input the sequence, and then q times you're gonna run a loop. So this is again a cool way of running the loop In case you are unaware of that, then this loop basically means is that, for example, you have a number, say 3. So and say while um, 3 minus 1. So again, so which will be equal to 2. Then similarly, it's gonna reduce to 1, and then finally 0. Now while 0 is gonna be false, so the loop is gonna stop running over here. So basically, this loop runs q times. Then we say that okay, we input the type in t variable and have treated the index as the k given in the question as index. Then simply if we are given the query of type 2, then we can print the answer as k minus 1, and by default we'll just update the value. So that's it from problem B. Moving on to the problem C, well, it says that Takahashi is a cashier and there's a cash register with 11 keys, and the keys are 00 and from 0 to 9. The cash register initially displays 0. Whenever he types the key 00, the number gets multiplied by 100. Whenever he types one of the other display number gets multiplied by 10 and then added by the number written on the key. Takashi wants the cash register to display an integer s, and we have to tell the minimum number of keystrokes required for the same. The constraints look pretty big, but don't get scared by this. It just simply means that these many digits can be present in the number. So basically, a normal string input will do the work. Now let's try to understand the problem statement in a little more better. So it's exactly same as we type numbers on a calculator. So for example, if we have a calculator and we want it to, let's say, display 5890900. So let's suppose this is the number that we want our calculator to display. Then let's see how actually it gets displayed on a calculator. So first of all, we'll be typing 5. So the calculator will initially show 0, then it will be showing 5. Then we type 8 so that the number becomes 58. But what actually happens is that it's 5 into 10, and then we can add 8 to it, which means 50 plus 8, which gives us the answer 58. And then we can type 9. So 58 will get multiplied by 10, which is 580. And then we can add 9 to it, which will be 589. And so on. So we have an extra key over here of 00. So what this number does is that it simply adds a 00 towards the end. So that's actually the real time, the real world implementation of a calculator. So we have to tell the minimum number of keystrokes. So let's think how we are gonna actually type this number. We're gonna use one keystroke for 5, another for 9, one for 8, then 9, then 0, then 9. And instead of pressing a 0 twice, the single 0 twice, we won't be doing that. Instead, what we can do is press the 00 key. So that's the only optimization required over here, that whenever you are entering a number and you encounter a 00, then it uses a single keystroke instead of two. So we have to tell what is the minimum number of keystrokes required to do the same. So it's actually pretty simple. So what we are actually doing is that number of characters, so basically number of digits minus number of double zeros encountered. So this is going to be exactly the same. So for example, we have again, let's say 58009005. So here, what are the number of digits? So 1, 2, 3, 4, 5, 6, 7, 8. So we have number of digits as 8. And how many times do we encounter 00? Once and twice. So this is 0. So basically we can say that we can enter the number in 6 keystrokes. Let's see how. We first press 5, that's 1. Then we press 8, that's 2. Then we type a 00, that's 3. Then we type a 9, that's 4. Then we again type a 00, that's 5. And then we can type a 5. So let's see how we can implement this in C++. So Here's the code. We first of all take in the number and put in a string because obviously that's too big to handle in actual number range as integer long long or maybe unsigned long long. That's just way too small to cater that huge number. Then answer is going to be the variable that contains a keystroke. Then we iterate through the string and we can say if the current number and the number so this denotes the current number and this denotes the number ahead. If these both number are 0 and we do not go out of bounds, in that case skip one character and then we can do an answer plus plus. So what this means is exactly what we are doing here. So for example, this is answer at 5. So this is our first iteration, we add it. This is gonna be our second iteration, we add it. This is our third iteration. I skip this one because the I plus one doesn't go out of bounds and we have two consecutive zeros. So I skip this one by doing a simple I plus plus, or maybe you could have entered. Let's do it this way only. So we can do a simple I plus plus, which means that I skip this iteration. Now my I is already pointing towards 4 and I do answer plus plus. So next time when I revisit the loop again while the incrementing condition, so I increment I twice instead of one whenever I encounter a double zero. So in case I have a 580000, so what's gonna happen is uh, so answer becomes 1 for 5, then 2 for 8. Now I encounter this, I'm gonna skip this 0 and answer becomes 3 over here. Then we again increment our iterator, that's I, and again I skip this 0 and we have an increment. So answer will be 4 and that's where we stop the loop, and then we can simply print the answer. Let's discuss problem D now. Let's get started by discussing the problem statement first. So we are given a string that consists of lowercase English letters, an opening and a closing parenthesis. And it says that the string is said to be a good string if you can make it an empty string by doing the following procedure. First, remove all the lowercase English letters and then repeatedly remove the consecutive opening and closing parenthesis pair. So basically, this means that we have a valid parenthesis string, that's the standard term, and we have some lowercase English alphabets embedded inside it. So let's take an example. So if we have the string uh, this is the same string. So first step, we are gonna remove all the lowercase English alphabets. So the string will look like this, and we can see that this is a valid parenthesis pair. How do you know this? We first remove this consecutive pair of parentheses, which will leave us with another consecutive pair of valid parentheses, and then we'll finally have a null string. So this is a good string. So it's an example for the same. Now you are given a good string. So it's guaranteed that we already have a good string S as an input to the question. And we denote its ith character by SI. So that's again a standard stuff. For each lowercase English alphabet, we have balls with the letter written on it. Additionally, we have an empty box. Okay. For each of the letters of the string, we perform the following operations. So if SI is a lowercase English letter, we put a ball with the letter written on it into the box. Okay. And if the ball is already present in the box, then Takashi is gonna faint. Okay. If there is an opening parenthesis, we do nothing. And if there is a closing parenthesis, we gonna do something that's written in pretty, um, let's say, not so friendly language in here. I'll explain that with an example. So, for example, let's take the same string, that is this one, and we have a box over here. We are also given a box. So we start by doing this. We encounter an opening parenthesis, we do nothing. Then another, we again do nothing. Then we have A. So inside the box, we are gonna put a ball with A written on it. Now, once we encounter the closing parenthesis, we search for the last parenthesis, the greatest, we search for the opening parenthesis that this bracket makes a pair with. So that's exactly what it's written here in some mathematical language, that we have to choose the greatest j less than I such that j through the ith characters of s form a good string. So we can say that this is going to form a good string, and j is also the greatest number because let's suppose if we have something like this, and for this particular parenthesis we have to choose this one because this is greater than this. However, this part, sorry, this part and this part both form a valid good string, but we have to choose the greatest. So this parenthesis will be the one chosen. So this in simple language means that you have to simply get the balancing pair of the current parenthesis. So we choose this, and once we encounter the closing parenthesis, we're gonna pop out all the stuff uh, till the balancing parenthesis. So basically, we are gonna pop out this a, and then we encounter a b. So we're gonna put b inside this, and then we encounter a, we put a inside this, and then finally we encounter a closing parenthesis which has a matching parenthesis over here. That means we are gonna pop b and a both. Let's take another example. So first of all, we encounter an opening parenthesis, we do nothing. Then we encounter an A. So we'll be having our box and a ball with A written on it will be inside our box. Then we encounter another opening parenthesis, we do nothing. Then we encounter B, we're gonna insert a ball with B written on it. Then we encounter A again. But look, this time we already have a ball with A written on it inside the box. So in this case, he's gonna faint, and if he faints, we're gonna print no as the answer. Otherwise, we're gonna print yes. So let's see how we can implement this thing. Now, pretty clearly, we already get an intuition of valid parenthesis problem. So in that problem, I'm gonna explain that real quick. So we are having some parenthesis and we maintain a stack. So that's a standard way of doing this. We can also maintain a counter variable for that, but for now we're gonna use a stack because that's what we're gonna use in this problem. So we're gonna maintain a stack, and whenever we get an opening parenthesis, we're gonna push it inside the stack, and whenever we encounter a closing parenthesis, we are gonna pop a opening parenthesis from the stack. So as I, and let's take it 0, 1, 2, 3, 4, 5, and let's have our stack over here. So when we encounter 0, we're gonna push the opening parenthesis. Now when we encounter, when our I becomes 1, we encounter a closing parenthesis. So we're gonna pop this. Then we encounter an opening parenthesis when our I becomes 2. Then we're gonna push it inside the stack. Then I becomes 3 and we push another opening parenthesis inside the stack. Then we encounter a 4, which is a closing parenthesis. So we're gonna pop this one. And at last we get 5, and we're gonna pop this parenthesis as well when our I becomes 5. And in last, if we have our stack empty, if stack is empty at the end, and we always have something to pop when we encounter the closing parenthesis, in that case we can say that the given string is a good string. Let's see how we can modify the previous solution to solve the current problem. So we're gonna maintain a stack. So we will be having a stack, and this is gonna basically tell us what this stack is gonna contain is that all the balls that are present in the box um, till the last matching parenthesis, till last match. So basically, if we ignore this these parentheses for now, then the stack would look something like this. That okay, this is the A that's gonna get pushed. Or let's actually make this thing a little complex. B, C, and then D, and uh, so so in case we have a string like this, then we're gonna first push A, and then we encounter another opening parenthesis. So whenever we encounter a closing parenthesis after this one, we can be pretty sure that the content after this particular parenthesis will get popped off, and the ball with a written on it will still stay. So that's gonna push deep down inside the stack and gonna come out at the last. So we're gonna push B and C over there, and then we encounter another close opening parenthesis, and similarly, uh, and like using the same logic, we can be sure that D will be popped whenever a closing parenthesis is encountered. So D comes over here, and we encounter a closing parenthesis. So which means that content till this particular parenthesis will be popped off. Which exactly is the content at the top of our stack. So D will get popped off. Then checking for this parenthesis, this is the matching pair, and we can be sure that B and C will gonna pop off, and finally our A gets popped off. Now, along with this stack, we'll also have to maintain a set or a map type of stuff. So I'll be using a stack, a set along with this to have all of this data combined at one place, and I'll be easily able to check if the current ball exists in the stack or not, in the current box or not. Let's try to understand the approach using this example. So we're gonna have a set which is basically denoting the box, and we also have our stack which is gonna denote that what content is to be added is currently present in this set, and if we encounter the closing parenthesis, then what is supposed to be popped off. So first of all, we get A. Okay, so A will be on the top of the stack. Then we encounter closing parenthesis. Then we're gonna remove everything from the set that is present at the top level of the stack. So we're gonna remove this A, and we're gonna pop this A off. Then we have B and A. So balls with written B and A will be inside the box, and BA also go inside the stack. Then we encounter the closing parenthesis, and we're gonna delete B and A from the box and remove it from the stack. And in case we are able to do all of this without ever fainting, basically, if we don't have to enter something inside this set which is already present there, in that case, we can be sure that this thing can be done. Otherwise, the Takashi will fail and will print a no. So let's hop on to the code. And there's a string s that's the given input. Then we will be having a stack named v, uh, the one used to tell that what was the last thing pushed inside the box, and the one that will have to remove from the box. The box is I'm gonna use a set data structure for that, so that I can easily handle the insertion, deletion, and check stuff. Um, then I'll simply input the string, and I'll uh, make sure that the current string is good and is enclosed inside the parenthesis. Then I loop through the string, and I see if there is an opening parenthesis. I'm gonna push an empty string to the top of the stack, so that I can further, if I encounter an English lowercase English alphabet, then I'll be able to um, push it on the top of the stack without bothering if it's empty or not. If it's a closing parenthesis, in that case, I'm gonna remove the topmost stuff of the stack from my box and also pop off that particular section. And in case I encounter a lowercase English alphabet, then I first of all check if it is already present inside the box. If yes, then I'll simply print no and return. Now, no, I defined it above, and no and yes. And then finally, I say that okay, if it is not currently present, then insert it inside the box and also insert it on the top of this stack. So if everything is good, then we have already guaranteed that the string will be good. So we don't need to check if stack is empty or stuff like that. Then we simply print a yes and return. Otherwise, if we encounter the same lettered ball inside the box, we're gonna print no and return. So the explanation for problem D was pretty long, but I do think that you would have understood it pretty well. Still, in case you have any doubt in any of the problems, then you can then feel free to ask me in the comment section below. Do give a thumbs up to this video and subscribe to this channel. Also, I would highly recommend you guys to implement each and everything that you see in this video or anywhere learning, so that it comes really, trust me, it's gonna really come handy while uh, solving the contest. Thank you.